What you're seeing on the screen, though, however, is the last section of the syllabus that deals with the chemistry of the elements. Just to say that in this section, really, you don't have much calculations to do, I think. Actually, I don't think you have any calculations at all to do. It's more about explaining why, explaining, what would you say, physical properties or observations, right? So you're explaining why something is a solid, why something is a liquid or gas, or why it reacts with this or whatever the case might be, okay? So this is actually the first part of the syllabus for that. So see there, module 3, chemistry of the elements, right? And you have period sodium to argon, and see, those are the objectives. Students should be able to explain the variations in physical properties of the elements in terms of structure and bonding. In other words, they're not just asking you about the physical, the state of matter of the elements from sodium to argon. And let me see, tell me what you're seeing on the screen now. At period 3, which would be sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, right? And clearly, at the left of the periodic table, you have the metals. And then as you go across, you go into the metalloids, such as silicon, then you go into the non-metals, phosphorus, sulfur, chlorine, and argon. And so the state of matter of these species, of course, all metals are solid except mercury. So you're expecting that sodium, magnesium, and aluminum would be a solid. Silicon is also a solid, I think. Yeah, silicon is also a solid, right? But then, and phosphorus can be a solid too. Sulfur can be a solid, and chlorine is a gas, and argon is a gas. So you can clearly see that you're moving from solid to gas, pretty much. Okay. There's no liquid in this group, so it's just solid to gas. They're not only asking you to say, okay, sodium is a metal, chlorine is a gas. They want you to say why sodium is a metal and chlorine is a gas. See it right there? Explain the variations in physical properties across the period in terms of structure and bonding. So why is sodium a metal? Okay, sodium is a metal because it has strong forces of attraction between the particles. It is metallic bonding, and metallic bonds are strong. Okay, notice over here for the explanatory notes, they say that include reference to melting point and electrical conductivity, which simply means that, okay, let me just clarify the chlorine one. So why is chlorine a gas and sodium a metal, a solid? And so we said for sodium that it is metallic bond, and metallic bonds are strong, so the particles are held together by strong electrostatic forces of attraction. For chlorine, no, chlorine is a gas because the particles are held together by weak van der Waals forces. So you have induced polarity to hold the particles together, and these bonds are very weak, so therefore chlorine is a gas. And same thing for sulfur and for phosphorus. So for the metals have strong electrostatic forces of attraction. In other words, metals lose their valence electrons to a sea of electrons. So what you have happening inside that metallic structure is that you have a cation, and I'll show you that now. You have a cation, Ca, C+, right, which is connected to an electron, which is connected to a C+, and then you have a cation there, so and then you have an electron there, and then you have an electron there. So you have attraction between the positive and negative species. So that's why we call it an electrostatic force. Electrostatic means that you have a positive and a negative, right? And this is the situation for the metals. So metallic bonds are very strong. And because the bonds are strong, they are solids. And because the bonds are strong, they have high melting points and high boiling points. That explains those features or characteristics. Now, along with that, And I'm jumping a little bit and mixing it and stuff. Along with the fact that they have high melting point, high boiling point, they're solids, they're also dense because these two particles come close together. The electron pulls them close together because of their mutual attraction for the electrons. So this cation here is attracted to this electron, so it draws close to it. This cation is attracted to this electron, so it draws close to it. So what you find is that the cations are close together. And when you think about density, what you're thinking about is closeness of the particles. Are the particles close or are they far away from each other? And in the case of metals, they are close because of the strong force of attraction there. Okay, for chlorine now, chlorine is going to be weak interactions, weak van der Waals forces, and so therefore it's going to be a gas. And because it's a gas, it has low melting point, it has low boiling point, and it is low density as well, because the particles of a gas are, of course, as you know, from fourth form, far away from each other, right? The particles of a gas are far away from each other. Okay, now you'll notice it also speaks about electrical conductivity. We know that, let's go back to the periodic table. We know that the metals conduct electricity, sodium, magnesium, aluminum, they conduct electricity in the solid state. Silicon is a semiconductor. And you'd know this because silicon is in your phone, it is in your TV, in your computer, every single thing, right? Phosphorus and sulfur don't conduct electricity and the others do not, okay? Because metals conduct electricity because they have free delocalized electrons. Let's go back to the drawing. Where's the drawing now? Oh yeah, here it is actually, but let me go back to the thing. So these electrons that you see in the nuclear, in the metal bonding, they are free to move around the structure. And once you have electrons that are able to move, then they can conduct an electric current. Okay, silicon now has within its structure some freeness of electrons, and that is why it is also able to conduct electricity somewhat, but it's not like as good as metals. Phosphorus, sulfur, chlorine, and argon do not have that luxury. They do not have ions in solution and they do not have free electrons, so they do not conduct electricity. Okay, and atomic radius, so let me go back to the periodic table. The atomic radius from math, as you know, the atomic radius is a distance from the center of this circle to the perimeter or the circumference, whatever you want to call it, the circumference, right? To the circumference, okay? So it's the same thing with an atom. Same thing with an atom. The atomic radius is the distance from the nucleus to the outermost shell, which is the valence shell, right? As you go across the period from sodium to chlorine, the atomic radius decreases. And you're going to have to explain why. The reason for that is, as you go across, the electronegativity of the elements increase. And this is where the electronegativity is going to come in now. See, it says electronegativity there. The electronegativity of the elements increase. What is electronegativity? Electronegativity is the ability of an atom to pull electrons towards itself. Why is an atom able to pull electrons towards itself? It is able to do that because it has something very positive within its structure. The only thing that can pull an electron is something positive. Okay, only electrons are attracted to positive things. Protons are not attracted to positive things. Okay, so because inside the nucleus of the atom, it is positive, it is able to pull electrons more. So what I'm basically saying to you here is this: as you go across the period from sodium to chlorine, you're adding electrons to the same shell. It is the same third shell that you're adding electrons to. Not only are you adding electrons, but you're also adding one proton each time. And remember, protons are positively charged, okay? So as you add the proton, the nucleus becomes more positive. Think about the nucleus like a magnet, which is pulling these electrons, okay? So imagine now you have a magnet, and let me see if I can find I don't want to come out of the page. Imagine now, I'm going to clear this. Imagine you have a magnet, right? You have a magnet right here. And then you have electrons right there, okay? Or steel. The steel represents the electrons and the magnet represents the nucleus, which is positively charged. Now imagine you have that magnet and you keep, the magnet keep getting bigger and 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 bigger. And what is happening as the magnet is getting bigger is that the electrons, which is it is attracted to, keep being added to the same distance away from it, right? The electrons are still being added the same distance away from the magnet. So that distance does not change. So what is changing is the size of the magnet. So the magnet is getting stronger and stronger and stronger and stronger. And because it is getting stronger and stronger, it is able to pull those electrons more. So these electrons that are out here are being pulled closer and closer to the magnet, which means that the distance from the magnet to the circumference gets less and less and less the bigger the magnet becomes. How does the magnet get bigger? It gets bigger because you're adding protons to it. And the protons are being added as you move across the periodic table. So as you move across the periodic table, the atomic radius decreases, the electronegativity increases, okay? So the electronegativity increases, meaning that chlorine has a greater love for electrons than sodium. And as a result of that, the atomic radius decreases, okay?